Hey there, it's Shannon Matchick Myers, and today we'll check out integrals requiring the use of trig identities. Now, keep in mind that this is just a little small part of the section on trigonometric integrals, which is techniques of integration. So the assumption is, you've learned some of the tricks prior. So these are just a few more tricks for you to add to your collection. And let's get to it. How it works, part one, product to sum identities. So this is the case where if two different angles occur in the integral, we use the following identities. So if you have the sine at m times x times the sine at n times x, that's going to be 1/2 times cosine at, you take the difference between m and n, that's times x, and then you subtract cosine at the sum of m and n times x. Now, if you have the sine at m times x times the cosine at n times x, again, it'll be 1/2. And then this time, the sine function will be in there. You've got the difference of the two angles times x, and then plus sine times the sum of the two angles times x. And then if you have cosine at m times x times cosine at n times x, you're back to having the cosine in both, and there'll be a plus sign in between them. So now this will be the difference of the two angles times x plus the cosine of the sum of the two angles times x. So let's take a look at an example. I'm going to warn you ahead of time. I mean, these numbers don't turn out super friendly for as far as the doing all the angles by hand, but we'll go ahead and do it. It reviews reference angles a bit. All right, so this will be equal to the integral of pi over 4 to 2 pi over 3. Now we have the sine times the cosine situation with different angles. So there'll be a 1/2 on the outside. I'm doing that from the formula. And then we'll have sine at 7 minus 4 times x plus sine at 7 plus 4 times x with respect to x. So this is going to be 1/2 times the integral from pi over 4 to 2 pi over 3. This is just going to get to sine of 3x's plus sine of 11x's with respect to x. Good so far? Excellent. All right. No pun intended. And so we'll have 1/2. Now we're integrating. So we'll get 1/3. And that'll be negative cosine at 3x minus 1/11 cosine at 11x. This will be evaluated from x equals pi over 4 to x equals 2 pi over 3. Now, just to get some of these fractions out, let's get a common, let's just get a common denominator as it is. So if you multiply all three of them together, you get 66. sorry. Yeah, So we'll have, I'll do it like this. 1/2 times 1 over 33. So I'm basically going to get a common denominator between the terms inside. And so I'll have 11 times cosine at 3x minus 3 times cosine at 11x. And that's going from x is pi over 4 to x is 2 pi over 3. Good so far? Trust me, I did it the other way and it was just really ugly. So now putting these together, we have 1 over 66. Now, here we go, upper limit of integration. We will have 11 times cosine of, when I plug in 2 pi over 3 for x, I get just 6 pi over 3, which is 2 pi. We good so far? And then minus 3 times cosine at 22 pi over 3. That's my upper limit. Lower limit of integration will be 11 times cosine at 3 pi over 4 minus 3 times cosine at 30, let's see, pi over 4, so 11 pi over 4. Are we good so far? Excellent. So now we will have 1 over 66. Cosine of 2 pi is 1 because 2 pi is coterminal with 0. So we're going to have 11, so this is 1. Now cosine of 22 pi over 3, so every time you go 2 pi around, you land at the same spot, right? So 6 pi over 3 is 6 pi over 3 is 2 pi. And so if you can go around 3 full times, that's equivalent to 18 pi over 3, all right? And then you have 4 pi over 3 remaining. So cosine 22 pi over 3 is coterminal with cosine of 4 pi over 3. And cosine of 4 pi over 3 is negative 1/2. Now, minus 11 times cosine of 3 pi over 4. So cosine of 3 pi over 4 goes in that second quadrant, so it's going to be negative. And I'll write it the way you're probably used to seeing it, as negative root 2 over 2. 1 over root 2 is fine with me. Negative 1 over root 2 is also fine. Now I distributed the minus to 1, right? And now when I distribute the minus to the other, it'll go positive 3. Now cosine 11 pi over 4 is going to be coterminal with, so 8 pi over 4 is 2 pi, and so it's going to be coterminal with cosine 3 pi over 4. Good so far? You know, it's a little weird. All right, and cosine at 3 pi over 4, we just did that, right? And that was negative root 2 over 2. Cool, cool? And so this is just kind of a note. Coterminal means they all have the same trig outputs. So then we'll get 1 over 66 times, let's see, we have 11 plus 3 halves plus 11 halves root 2 minus 3 halves root 2, and combining, let's see, the 11 and the 3 halves, I believe, will give us 25 halves. And then when we combine the root 2's, they're already common, so we'd end up with 8 halves, which is 4. So plus 4. Actually, let's keep it in terms of halves, then we can pull it out. So we would end up with plus 14 root 2 all over 2. And then pulling out another half, we would have 1 over 128. No, sorry. That's going to be 132, I think, right? Yeah. 132 times 25 plus 14 times root 2. Groovy? And that's the result. Now, here we go. Another great technique is to convert all terms and factors into sines and cosines. This will often simplify the integrand, the stuff in the integral, quite a bit. So here we go. We have tangent squared at x over secant at x, all that to the 5th. So then, if I rewrote this, tangent squared at x is going to be, whoops, sine squared at x over cosine squared at x. Now, 1 over the secant function is the cosine function, so we'd have cosine to the 5th at x, and then times dx. So this one will end up being sine squared at x times cosine cubed at x dx, and then this ends up being one of the ones we were working with, right? So I'm looking at this. I have an odd number of cosine factors and an even number of sine factors. So I'm going to reserve a cosine factor, which means my g of x will end up being sine at x. So g prime at x will be cosine at x. So here we go. We'll have sine squared at x times cosine squared at x times cosine at x with respect to x. This will give us, I'm going to write the sine at x in parentheses so we don't mix up which one we want to have as a composite function there. And then rewrite our cosine function as 1 minus sine squared at x. And then we still have that other factor of cosine at x waiting in the wings. And now we will get sine at x squared. So I'm multiplying sine at x squared times 1 times cosine x dx. And then sine at x squared minus times, so then I'll make a new integral, minus sine at x squared times sine at x squared times cosine x dx will give us sine at x to the 4th power times cosine at x dx. So on each of them, I have my g prime all ready to go. So this will be 1/3 sine cubed at x minus 1/5 sine to the 5th at x plus our constant of integration. Cool, cool? All right, last but not least, we have this wonderful, wonderful creature here. So I've got cosine at x in the denominator, right? So what I'm going to do is I'm going to turn that sine squared at x into cosine squareds. So we have 1 minus cosine squared at x from the sine squared at x minus cosine squared at x all over cosine at x with respect to x. So then I'll have the integral of 1 minus 2 of those cosine squared at x's over cosine at x with respect to x. But this is equivalent to 1 over cosine at x, which is secant at x dx, minus the integral of 2 cosine at x dx. So all I did was I divided through by cosine and separated the integrals. Now, don't forget, we have a basic integration formula for the secant function. So we'll get natural log absolute secant at x plus tangent at x minus 2 times sine at x plus our constant of integration. And then we're all done. Isn't that groovy? All right, well, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. If you like what I'm doing, feel free to subscribe, hit the like button, share the video. Talk to you soon. Bye.